All right, let's dive straight into this explainer. Today, we're doing something really fun. We're treating chemistry not just as a science, but as a universe governed by strict, logical, and honestly, beautifully mathematical rules. If you've ever stared at a chemical reaction and thought, how do they actually know what's happening down there? Well, you are definitely in the right place. We're starting with what is arguably the ultimate problem in chemistry. How in the world do we count atoms when they are literally too microscopic to see? It's a massive hurdle. Figuring out how to bridge that invisible microscopic world of atoms and molecules with the macroscopic world. You know, the world of grams, liters, and beakers that we can actually physically measure in a lab. To answer that, here is our roadmap. We'll start with precision and dimensional analysis, move right into the laws of chemical combination, explore Dalton's atomic theory, master the mole concept, and finally, decode empirical and molecular formulas. Section 1. Precision and dimensional analysis. Setting the baseline. Look, you simply can't play the game if you can't accurately measure the board. Before we even think about weighing atoms, we need a flawless system for converting units. Thankfully, the factor label method is brilliantly simple. First, you just find your conversion factor, like knowing 1 inch is exactly 2.54 centimeters. Second, you multiply your starting quantity by that factor. And third, and this is the absolute secret to never messing up, string them together in a way that your preceding units cancel out top to bottom. It lets us safely convert literally anything without losing our mathematical way. Section 2. Laws of chemical combination. The governing laws. So now that our baseline measurements are locked in, we need to understand the 5 unbreakable laws that dictate exactly how matter is allowed to interact. Think of these as the rulebook for the universe. The first 4 laws, conservation of mass, constant composition, multiple proportions, and reciprocal proportions, are all heavily focused on mass and weight. But that 5th one, Gay-Lussac's law, is a bit different. It deals specifically with the volume of reacting gases, basically saying that under the same temperature and pressure, gases will always react in simple volume ratios. And the law of reciprocal proportions is perfectly illustrated when we look at how magnesium, oxygen, and hydrogen interlock. Think of it like a triangle. If hydrogen and oxygen combine with a fixed weight of magnesium, the ratio in which they do that will either be exactly the same or a simple multiple of the ratio they use when combining with each other to make water. It's like watching a perfectly tuned mathematical puzzle just snap together. Section 3. Dalton's atomic theory. The fundamental particles. Knowing the rules for combining matter is great, but what exactly are the pieces on the board? Well, back in 1808, John Dalton published a theory that totally flips science on its head. He proposed that all matter is made up of these tiny, indivisible particles called atoms. He argued that atoms of the same element are completely identical, they combine in simple, whole number ratios, and crucially, they are never created or destroyed in reactions. This was huge because it finally gave us a physical explanation for all those governing laws of mass we just talked about. But wait, it turns out mass isn't perfectly uniform across every single atom of an element. Let's use carbon as an example. Naturally occurring elements have isotopes. Carbon-12 makes up almost 99% of it, but carbon-13 and 14 are out there naturally too. So, to get the atomic mass we actually use on a daily basis, we have to calculate the average atomic mass, factoring in the natural abundance of all these different isotopes. Section 4. Mastering the mole concept, the ultimate counting unit. Okay, here's the big question. If atoms have these incredibly tiny, specific masses, how on earth do we actually count them in a real-world lab? The answer is this mind-blowing number right here, 6.022 times 10 to the 23rd power. To put that crazy scale into perspective, if you had that many marbles, they would cover the entire Earth miles deep. It's Avogadro's constant. Just think of it as chemistry's version of a baker's dozen. A dozen is always 12, whether it's eggs or donuts, right? Well, Avogadro's number is the exact amount of particles you need to translate atomic mass into actual usable grams. We call this massive amount a mole. By definition, it's the amount of a substance containing exactly as many particles as there are atoms in exactly 12 grams of the carbon-12 isotope. This idea is an absolute game changer. It perfectly bridges the microscopic mass of one single atom to the macroscopic weights we scoop onto a scale. 1 mole of carbon atoms weighs exactly 12 grams. It is literally the ultimate translator. And here's a fun fact. The mole doesn't just apply to weight. It applies to physical space, too. Thanks to Avogadro's hypothesis, we know that 1 mole of any ideal gas at standard temperature and pressure, or STP, will always occupy exactly 22.4 liters of volume. It doesn't matter if it's oxygen, hydrogen, or carbon dioxide, 1 mole of it will perfectly fill up a 22.4-liter container.
Section 5, Empirical and Molecular Formulas, the final blueprint.
All right, final stretch. This is where we see how chemists write the exact molecular blueprint for any compound in the universe. But first, you have to know the difference between two types of formulas. The empirical formula gives us the absolute simplest whole number ratio of atoms, like CH, but the molecular formula, that reveals the true exact structure of the molecule, like C6H6 for benzene. So empirical is your base ratio, while molecular is your actual building instruction. So how do we calculate it? The math here is deeply satisfying. You start with the percentage composition, say 20% carbon and 46.67% nitrogen. You divide those by their atomic masses to get the atomic ratio. Then you just divide all of those by the smallest ratio to find your simplest whole numbers. Step by step, the math cleanly spits out the empirical formula, CH4N2O. And to cross the finish line and find the true molecular formula, we just need to find a simple integer called N. You get N by dividing the compound's actual molar mass by the mass of our empirical formula. Once you've got it, you just scale that empirical blueprint right up. If N is 2, our CH4N2O suddenly becomes C2H8N4O2. Boom! We've just unlocked the exact chemical recipe. And that brings us to the end of our roadmap. You now know the rules of the chemical game, from those basic dimensional analysis conversions to the unbreakable laws of mass, all the way to using the mole to build exact molecular blueprints. But I want to leave you with a thought. If an idea as brilliantly simple as the mole let us translate the invisible world into our macroscopic reality, what new secrets of matter are we going to unlock when we develop even more precise ways to measure? Thank you so much for exploring this with me today. Keep questioning and keep exploring.